Good evening and welcome to this evening's webinar, Specialist Mathematics Exam Readiness, hosted by Texas Instruments Australia. My name is Rodney Anderson. I will be your host for the webinar. One of the panellists tonight is Bojana Graham, a very experienced presenter and Australian T-Cube instructor. Hello, Bojana. Oh, she's there. I hope she hasn't fallen out. Oh, there she is. Hello, Bojana. And then the first presenter for tonight is Raymond Rosen, and you'll see that he's an author of Wiley Specialist Mathematics, very experienced gentleman there, and he's going to commence with his part of tonight's webinar. Over to you, Raymond.
Okay, thank you very much. Now I have to share the screen. Okay, all right. Well, welcome everybody to tonight's webinar. My name is Raymond Rosen, and tonight I'll be looking hopefully at a few ideas of functions and graphs and some probability and statistics. So let's get straight into it. First of all, some typical sort of multiple choice type questions for specialist maths. Although I haven't got listed various options for the multiple choice, we'll just work through these. Some of these we'll work through on a notes page, some of them we'll work through on a calculator page. So for example, the first question, find the domain and range of the function f2 r cos x on 3 minus 1 plus pi. So for this function, I've already defined some of the functions to save a bit of time, but the main idea I want to get across here is the domain function, a fairly new feature. However, the domain function is not available from any of the menu functions. If you want to get the domain function, you actually have to go to the little book or the catalogue icon here. So if we press this one and scroll down, just hit the D command, which I've already been on, so we actually have to find the word domain. Down the bottom there, we see a bit of a hint on how to use this with expression and var. So if I just hit the domain, and because f of x is already defined, I could actually just go from the var key to get the f of x command. So there's the function automatically defined, and there's my domain. So my domain for this function is 0 to 6. Now, we know that r cos, r sin, and r tan functions are all one-to-one functions. So in this case, there is no range function. If I want to find the range, I can just work out f1 of 0, and also f1 of 6 at the other endpoint. So therefore my range is pi to 3 pi. I've also sketched this graph on this function here, and notice that on the x and the y axes you can label your coordinates with pi's and the intervals in terms of pi's. So a nice little feature, and also putting in the endpoints and the endpoints with their respective coordinates. So that's a nice little function, which, as I said, typical multiple choice type questions in the specialist exam. Another new sort of type of question that they've often will have, is discuss the features of the graph. Now, in other words, they want to know where have we got asymptotes, where, what are the equations of the asymptotes and things like that. Once again, I've defined the function f of x, f1 of x to be x squared minus 2x minus 8 over x squared plus 6x plus 8. Now, the denominator, x squared plus 6x plus 8, most students will think, well, okay, if the denominator is 0, then therefore we're going to get vertical asymptotes. But that's not necessarily true in this situation. So let's go solve when the denominator equals 0 for x. So a bit of an investigation here. The denominator is 0 when x is minus 2 or minus 4. Let me just try to evaluate the function at minus 4, which is obviously undefined, and obviously evaluate the function at minus 2, and it's also undefined. However, there is a bit of a difference between them. Let's investigate some limits here. So first of all, we'll get the limit command, which we can get from the calculus menu. We can also get it from that little template there. Well, first of all, to find horizontal asymptotes, I want to see what happens as x approaches infinity. So if we say x approaches infinity, type in the infinity command from the little template there as well, of the function f1 of x. That gives me y equals 1 as a horizontal asymptote. But let's try that again for these two strange values here. Let me just repeat that one for x equals minus 4. Well, that one's certainly undefined, but what about at x equals minus 2? This one actually exists. So although the limit exists at minus 3, the function is not defined at minus 2, we do not have a vertical asymptote at x equals minus 2. In fact, if we look at the original function, and when I just type it in, it has actually simplified it. It has cancelled the factor of x plus 2 in the numerator and the denominator. This little symbol here, this little triangle, Whenever you see this, it means warning, warning. You know, something may be not quite right here, or it's right, but the factor has cancelled. So in fact, this graph, when we sketch it, I've already sketched it previously, or to summarise the features, the graph has a horizontal asymptote at y equals 1, a vertical asymptote at x equals -4, but at x equals -2, there is what's called a point of discontinuity. So when we look at the graph, now the calculator won't draw in these horizontal asymptotes. These have been drawn in previously with the horizontal and the new straight line features. I've also put in this little point here at -2, -3. The calculator will not put that in, but I think it's nice to see that this graph does have a hole in it, or what's called a point of discontinuity at that point. So a very nice little feature of these graphs to investigate the limits and to see, you know, what's happening for these functions. All right, another nice little question that's also very common is having a relation to find the gradient of the normal to the curve at the point where it crosses the y-axis and y is negative. So once again, we actually have to find the coordinates where y is negative and it crosses the x-axis. So let's just type, I've already typed in that function there, or that relation. What I want to do now is do the implicit differentiation. Implicit differentiation is available from the calculus menu. We don't actually see it, it's hiding down here somewhere. Here it is, implicit differentiation. And let me just go up and highlight that to save typing it all in again. So implicit differentiation, the syntax however is comma x, comma y. So that will give me dy dx in terms of both x and y. But I want to find, if you recall what the question was, the gradient of the normal to the curve at the point where it crosses the y-axis. So what we can do is we want to do a menu, algebra, solve. We want to solve this equation for y when x is equal to 0. So when x is equal to 0, I'm going to use the slash command or the given command, whatever you like to call it, given that x is equal to 0. This gives me two values of y. The question was we wanted to find it when the fourth quadrant when y is negative. So basically what we want to do is we want to find the value of dy dx. Once again, use the given command at the point where x equals 0, and we type in the word and, only the point when y equals -2. Once again, that's not quite the answer, because that's the gradient of the tangent to the curve. Recall the question wanted the gradient of the normal. So the gradient of the normal, the answer, is the negative reciprocal of that. So the answer, gradient of normal, and we can actually just type in some text here with the comment command. So if I insert a comment, then this is actually ignored. So the gradient of the normal is -2 on 3. Okay. So again, nice little commands to use gradients of normals. All right, another common little question here, and this one's quite a nasty one, to express this in partial fractions. What do we want to do here? Well, basically we've got some horrible, nasty expression, and once again, to save a bit of time, that's on a notes page with the questions, I have defined this function to be r of x. Now, what I want to do here is basically just to see and factorise the denominator. So a couple of nice little commands that are available are menu, algebra, and what am I doing? I'm doing something with fractions here. What I want to do is I want to actually get what's in the denominator. So a nice little function here, get denominator. So if I just get the denominator of that defined function r of x, then that just extracts the denominator. So what I want to do now is just to basically factorise that denominator. So let me just go factor of that. We see here we've got a repeated factor of x plus 5 all squared and a non-linear factor, x squared plus 25. That just suggests what the partial fractions decomposition might be. Now, to actually see the partial fractions decomposition, this is sort of a strange one, not probably what you'd expect to do. If we just go menu, algebra, expand. Now, I wouldn't really thought if expanding is what we want to get here, that when we expand r of x, that's what we've got. We've got the linear factor, 3 over x plus 5, plus minus 13 over x plus 5 all squared, which is the repeated factor, and these two could have been over 1 as minus x minus 2 over the non-linear factor. So often they'll have exam type questions in terms of A's and B's and things, but that doesn't matter. You can still do these. You might not be able to solve for these sort of factors. But, you know, I really don't like the expand, but that's what gives us the partial fractions decomposition. All right, another idea is solving type 3. This is the new type 3 differential equation. dy dx equals a function of x times a function of y. And if it's a general solution, then this will involve a constant of integration. Often the solution to some of these may not be expressed exactly as a functional dependence of y in terms of x. We might have just an implicit differentiation relation. Sometimes we can actually rearrange and make y the subject. If we've got some further information, such as y of x0 is y0, then this will enable a particular solution to be found. And once again, sometimes we can rearrange to make y the subject. Okay, so let me just try to solve this one, solving a differential equation. I'll actually solve this one on this notes page. Those questions are already typed up in the notes page. So on a notes page, if you want to insert some text or some maths to be done, you can just insert what's called a control M. So we insert a maths box, or control M, as you can see there. Now, the command for the differential equation solve, this menu is now different, but once we hit the calculations menu, it's the same menu we get on the calculator page. So what we want to do here is differential equation, DE solve. So differential equation solver. Here we have to know the syntax, so it's y dashed. To get the dashed command, we're going to get it from this button here. And if we scroll across, that's the dashed. So that's dy dx equals. Now we want to get a template for y over the square root of x. And we've got some initial conditions here. So we'll do a space and type in the word and y of 4 equal to minus 1, comma x, comma y. And that will give me the solution of this differential equation. Sometimes in some of these questions it will give an implicit domain for some of these type of questions. That's okay, that we can handle that. And so the domain is often given. All right, now the relationship between that is also similar to what's Euler's method and slope fields, and I think Bojana will have a look at a few of those. But here's another sort of typical question. If we've got a function f of x defined by fe of x squared, and g of x is an antiderivative of that function such that g of 1 is 3, find the value of g of 2. Now, in this situation, we can't actually integrate, no one can actually integrate the function e of x squared. That function can't be integrated. If we try to solve this question, this is the solution from a notes page, which I've cut and pasted using a PDF into a notes page here. We'll define the function f of x as x squared. G of x is defined by the integral from 0 to x of that function. Notice that I'm using a dummy variable here of u, which I think is a good, safe idea to use dummy variables. Now, the plus c is the important thing is we don't know what the c is. So we define g of 1 as equal to 3, so we substitute x as 1, and that enables me to find the value of the c. So c is 3 minus that integral. Now, although I've defined it from x to 0, the 0 is actually irrelevant. I could have said a there, because when I substitute back for the c, and now use some properties of the definite integral to change that minus into a plus by changing these two terminals, 0 and 1, and then another property of definite integrals, you can see that the 0 there just combined to make it x to 1. So we can then integrate between 1 and x, and although we can't actually do that integral exactly, we can, on the calculator, do that integral approximately by pressing Control Enter. So I think this is a nice little multiple choice type question here, because people often get these ones wrong. So let me just show you that even the calculator, as I said, no one can actually integrate that function. It can't be done. But in using the DE solve command, so let me just try that again with menu, algebra calculus, and DE solve. differential equation solver, y dashed. So I want to solve y dashed equals that function of e of x squared. So I'll type in e of x squared. And I have got an initial condition here, so I'll type in and y of 1 is equal to 3, comma x, comma y. Now, what's happened here? The function has given me a C8, because in the practice session I had it before. If I try that again, let's see what it comes up with. This time it comes up with C10. Don't know why it's coming up with these C10s, C12s. These are just sort of similar to things like when we do a general solution. They're just sort of like a counting variable. So what we can do now is we can define the function y of x to equal that function. That's a function defined by an integral. So let me delete the y equals there. And although that's the function defined by y equals, if I just try to evaluate that function at 2 now, we get the same answer that we got in my work solution over there. So I think that's a nice little question to actually demonstrate the use of functions defined by definite integrals. All right, one of the other new aspects of specialist maths this year is in the statistics area, statistics and probability. So I want to sort of move on to do a couple of worked examples of probability and statistics here. Now these are basically two formulas which are just basically on the formula sheet, combinations of random variables. E of x is mx, variance is x is x, e of y is my, variance is sy, t is ax plus by. Then the expectation you just multiply, but the variance you square them and add them. Now note that even if it was minus y, you'd still go plus minus 1 squared. Alright, so a simple little application of that is we've got cats and dogs, and say we've got the weights of cats normally distributed with a mean of 5 kilograms with a variance of 2.5 kilograms. Notice that the variance is kilograms squared, the units. The weights of a certain type of dog are normally distributed with a mean of 15 and 3.5 squared. Find the probability that the total of 4 cats and 3 dogs exceed 70 kilograms and the average of 5 cats exceeds 6 kilograms. So although this question is really nothing sort of new on the calculator, it's just an application of normal distributions really. So basically why I'm doing this question is so I can show a picture of my cat and a nice picture of a dog. So if ever you want to insert pictures in your files, it's very easy. Just copy them to the clipboard, open a notes page and click and paste them in, and you've got some pictures in your documents. So moving on with the maths of this, the C is a normal distribution, C being the weights of cats. Notice in the normal distribution we always quote the variance. So the variance was 2.5 and for dogs it was 3.5. Total of 4 cats and 3 dogs. Just work out the expectation and the variance, and then the normal distribution of the total, and we're just using normal CDF here. Okay, so people who are doing specialists need to know about normal CDF, which is done in the methods course anyway. So for the next part, C bar. Now this is another little formula. The variance due to the central limit theorem here, or we know that when we have lots of averages, the standard deviation is sigma on root n, or the variance is sigma squared over n. So here if we work out C bar, probability of C bar greater than 6, so the average of 6 cats will get that normal distribution. So they're nothing terribly new and exciting as far as just working out normal distributions from normal CDF. To work out normal CDF, it's from the A value up to the next value, comma, the mean, and comma, standard deviation. So just make sure that when you're doing this on the calculator, you're doing it with normal CDF standard deviation, but in the wording, remember, in the questions, you're quoting the variance as the common factor here. All right, so a new sort of question also in statistics and probability is this one, 95% confidence intervals. So another type of dog has got a mean of 20 kilograms and a standard deviation of 4 kilograms. What we want to do is find a 95% confidence interval. So to work out a 95% confidence interval, we have to know a little more about inverse normals and things like that. The Z value for 95% is 1.96, or plus or minus. That one should be minus 1.96. The formula, x bar plus or minus z alpha on 2, s on root n. Although we should be using the value of sigma here, which is the population variance, I'm actually using the standard deviation of the sample of 4 rather than the population. And that's okay because n is fairly large here. 25 is probably considered the borderline between a small and a large number. So working that out, x bar plus or minus 1.96 sigma or s on root n. Well, let me show you how we can get those results from the calculator. So on a calculator page, what we want to do now is work out this confidence interval. So, well, let's go menu. Where would this be? It'd be under statistics now, I imagine, and what we're doing is a confidence interval. So you don't have to remember any of these things, it sort of prompts you for yourself. So what we're doing here is a Z interval, which is a Z interval. So click on that. It's prompting us for my data input method. Now, there are two methods of entering the data here. The data is either data or stats. Now, data means that I'd have all the numbers in a list somewhere, and I get the mean and the standard deviation from that list of numbers. So, for example, if I had 25 numbers in some list, I would choose that from the list. But in this particular question, I'm going to click down arrow and choose the stats and click OK. So it's now prompting me. As I said, it's prompting me for sigma here, but I'm actually typing in S really for the standard deviation of this sample, not of the population. That's a bit of an assumption there, but I think it's okay due to the central limit theorem. X bar was 20, N was 25, and we can choose an appropriate level of confidence interval here for the confidence interval. 95% is the default, normally 95 or 99. And we do that, we get the lower value, 18.43, 21.56. And as I said, they compare with the values that we had over here, 18.43, 21.57 to 2 decimal places. So that's a nice new one of getting the Z interval for a confidence interval. Alright, so it looks like I'm right on time here. My last example I want to work through now is a hypothesis testing. So this is an interesting one. A fast food chain advertises that the large bags of chips have got a weight of 150 grams. Some students suspected that they were not getting enough chips in the bag. So they tested and they ate 25 bags of chips and weighed them very carefully and had the mean of the sample of their 25 bags to be 148.6 grams with a standard deviation of 6.3 grams. And at this we want to perform a hypothesis test, clearly stating our conclusions. Now, this is an interesting one. I haven't actually done this one personally myself. This is really just a made-up example. However, in class sometimes I do actually buy packets of chips for the students. You know, you can buy the bags with 100 grams and give the students and let them eat it and get a weighing thing from the chemistry, and you can weigh them to exactly, 1 or 2 decimal places. And the students love this when you do this in class because they get a free bag of chips and they get to eat them and weigh them. And then we actually perform the example on real-life application questions here. So what are all my values here? Okay, well again there's a nice little inserted picture. Let's get on with the maths of this. So hypothesis testing, what we actually have to do is we have to state what's called the null hypothesis. So the null hypothesis is what we're assuming. We're assuming everything is fine here. The null hypothesis, the mean of the population mu, is equal to 150. The alternative hypothesis, H1, some books call it HA, is what we're trying to prove here. And what we're trying to prove is we're trying to prove that we're getting less than 150. Now, when we do it less than or greater than, it's what's called a one-sided test. If we weren't sure it was less than or greater than, we would just say mu was not equal to 150, in which case it would be what's called a two-sided test. And I'll talk a little bit more about that one in a moment. So we've got all our sample statistics, X bar, the mean of the sample, mu, the population, what we assume, the standard deviation of the sample, and the number of bags, 25. So we work out the Z value, and the P value is the probability of that happening, assuming that mu is equal to 150. Now, although we can get all these results from the calculator, we still have to interpret these correctly, and that's where I think people often get confused. So let's just have a look at how we can actually perform this calculation on the calculator. Remembering, of course, that the calculator does not actually give us the results, we actually have to interpret them. So let me choose again on a calculator page, menu. What do I want to do this time? I'm doing something with statistics. Last time we chose stats test. Last time we chose confidence intervals. This time we're choosing stats test. So once again, we're doing a Z test here. We will do a T test if the value was less than 25. One thing that perhaps we can note for the methods people is that they actually do a one proportion Z test as well. But for the specialists, we're doing a Z test. Once again, a similar sort of thing, data input. No, we're not choosing data from a list. We've got the actual stats. So we'll click or tab to OK. So just tab between all these fields and click OK. Mu naught. Well, mu naught is the value we're assumed that everything is okay at, which is 150. Sigma, once again, we're approximating that by S, the mean of the sample, not of the population. X bar was the mean of the sample, which was 148.6, and N in our case was 25. Here again, we can choose the alternative form from the hypothesis test, HA, the alternative. In our case, it was a less than, so we choose the third option there. Tab to OK and press Enter. And there's all our results that we calculated before, the Z value and the P value as well. Notice that we're actually only looking in the one tail here. So there's the inverse normal. The P value can actually be obtained as the probability less than 148.6, with sigma, with the standard deviation being 6.3 on 5, because that's the square root of 25. Notice that if I set a standardized Z score from 0 to 1, that also gives me the same value there as well. And the 1.65 was the value that we looked at in the confidence interval. So in this question here, we can see that we've got all the values that we calculated previously on the page before, but we still have to interpret. The value of Z that we've been obtained is in this area here, which is the acceptable region. If we're in this taily region, remember this is a one-tailed, if it was a not equal to, then we'd have the symmetry on the other side. But in this situation, then we don't have evidence to suggest that the manufacturers are underfilling the packets, because our value of Z that we got was in here. When we've got a smaller value in here, then that would be evidence. But in this particular example, there is no evidence to suggest that the manufacturers are underfilling the packets. So we have got no reason to accept the alternative hypothesis. We have to no evidence to reject the claim. So we can't sue them thinking they're underfilling the packets. All right, I think that's sort of what I wanted to go through tonight. I've got plenty of other stuff, but I think we'll leave it to Bojana to look at some analysis type questions. So I hope you've enjoyed that little section with a bit of probability and the new statistics and a bit of the coordinate geometry and implicit differentiation stuff. So I'll hand over to Bojana and
Thank you.
All the best.
Thank you, Raymond. Thank you. Well done. Students would love going to your classes with the food on offer every now and then for analysis. So just seeing your screen come up shortly, Bojana, and it's still grey there for the moment. And yes, we see your screen now, Bojana.
So I actually wrote 2 extended response questions trying to incorporate new feature, which is the arc length, and doing it in 2 different ways, one with the function and one with parametric equations. So here is our first question when we have the arc 10x plus 1 defined for x values 0 to 4. We want to sketch the graph of this function. Then we want to sketch the graph of the inverse function on the same set of axes and find the point of intersection. Then we want to write down a definite integral expression for the area between those 2 functions and the point of intersection, and then we want to evaluate the length of arc from 0 to 4, again writing a definite integral and then evaluating to 3 decimal places. So we can define the function but I might actually try to do it live. So if I'll open a new document and I enter the function here as inverse tan of x plus 1, and again we can easily restrict the domain here being from 0 to x and 4. So that's our bit. We might change the window slightly just to see this function better. So I looked up a bit beforehand, and let's say to 5. And then if we want it to show a nice reflection later, we might also try to do zoom square. So I might put it a bit out of the way. Now, how would we now use the new feature on the calculator to draw the graph of the inverse function? We need to change the graph entry to relation. And if we do that, now we can type x equals f1 in y, and that graphs nicely the inverse function, which I might just do in a different color. So that's our inverse graph on the same set of axes. And if we want to find the point of intersection, we need just to do the do it again, menu, analyze, graph intersection, press, and go. Here, and I have the intersection to 2 decimal places. If we require different accuracy, that's how we do a different accuracy on the graph. But I go back and actually change it to float 3 because most of the time it will be probably 2 decimal places on the specialist paper. So, of course, I can sketch it and get the point of intersection. Still doesn't allow me to know what the equation is, but if I go to the calculator screen and I can use menu algebra solve, and I go solve x equals f in y, and we want to solve for y. What did I do here? F1, sorry. I don't have F defined as I had in F1 in y equals, so I get the answer, so students can see that this is actually the answer. If they do it by hand, they can later check. And if we go to this graph and open the graph screen and change it back to the graph entry function, and we can enter 10x minus 1. So this is just for the student to be able to see the formula, and it will draw a few more, but for this purpose just confirming that this is what the graph actually is. So if I go back to my prepared screen, so I did the same thing, and that is the graph. And now we can actually evaluate the area graphically here by using, as you know, we have the new feature bounded area, and we go between the graph and the x-axis from here to there, and then we repeat for the second bit, so that works nicely. But as we said, the students were supposed to actually write down the value. So what I did here, I solved f in x, which was my predefined function, with 10x minus 1. So just to have this value as the exact value, and I stored it as A, and then we need the sum of the two areas between, as we look again at the graph from here to here, just below our original function, and then between two graphs, so that's the formula, and that gives us the area 2.83, which is exactly the same as what we would have on the graph. Now for the length of arc, if we are in the calculator screen and we go to menu calculus, then we have arc length there, and my function was f1 in x, and the variable is x, and if I want to find it between 0 and 4, that's what we enter. Of course, so I have that done here in this screen. If the students are write it as the formula, they need to find the derivative of inverse 10 x plus 1, which is 1 over x squared plus 1. It still keeps that because I had that predefined, and then if they enter that using the formula as written on the formula booklet, we of course get the same value. So that is looking at the length of arc using this inbuilt feature arc length, which works with the function. And again, it can also be found in the catalog as they showed there. So we need to arc length here, and then it actually explains what the syntax is. So it's expression and variable and starting and ending point. So in case of any doubt, you can always go to the catalog and see what the particular entry is. So that was the first question, which could be a possible extended response question with areas and arc length. So the second question I have here is the question about the drone, very popular recently. So it is the question when the drone follows the path given by the parametric equations but crashes into a wall at time t equal 10. Assume all distances are in meters time in second. So we want to sketch the path of the drone. At what times was the drone flying vertically and horizontally? Calculate the total distance traveled. So again, it's the length of arc, but given in the parametric form. Find the speed and the angle at which it hits the wall. So what we can do here, again, I will open a new document to do it a bit from scratch. So we need a graphs document, and the graph entry this time is parametric. So we need to put t minus 3 sine of t, and then using tab we get to y1, which is 4 minus 3 cos t. And we need to notice here that by default it goes to 2 pi, but our time is actually up to 10. So I get this picture here, and again I can change the window settings to see the picture better if I later want to do some trace. So I might go -1 to about 8. And I hide that because we don't need that. Now, very nice feature on the calculator is trace and graph trace. So of course, if I enter 0, it tells me where it starts. So the starting position is 0 and 1. Then if I enter pi on 2, I get to another point. If I enter pi, I get to another point, and so on. So going back to my prepared question here, I actually drew the wall at this point because what we can do, we can find x1 in 10, which is this value, and then I again saved it as W for wall, so that gives us the area, the idea where it is. And now if I do trace, graph trace, and I enter 10, so that tells me that the drone hits the wall at the distance 11.6 and 652. And again, if we want a more accurate values, I could change the settings here, so it depends what accuracy is actually required. So these are a few features which are quite useful. So the next thing we can do here is, if we want the horizontal component of velocity, I actually have all that open, but close it a bit. So we need to differentiate the x1 in t, and if we do that, we get the horizontal component of velocity is 1 minus 3 cos t. And if we want to find when the drone is flying vertically, so then the dx dt is 0 and dy dx is not 0. So remember, when solving trig equations, we need to have a domain, otherwise it gives the general solution, and that is not telling us much, so it's probably a better idea to have control T. So these are the times when the drone is flying vertically, because dx dt is equal to 0. Doing the same with the vertical component of velocity, we get it's 3 sine t. This one makes a bit more sense if we put it in exact values, because it gives us the time 0, pi, 2 pi, and 3 pi. And if we go back here and enter, let's say, pi, enter, and if we, so we can actually see that at those points it is flying horizontally, and that makes sense with the graph as well. Now, the next thing we can do here is what I did. I differentiate in x1, and then I save that as x2 in t. So that gives me the horizontal component of velocity, and I differentiating 1y in t and save that as y2 in t, so that gave me the vertical component of velocity. So to find the speed, we go x2 in t and y2 in t. So these are the two components at time t10 when the drone hits the wall. And then to find the speed at this point, we simply find the square root of the squares of the sum of the squares of the components. And using simple trick, we can find the angle. So that is another thing. We can also do it using this is actually the definite integral now for the arc of length. So we're going 0 to 10, and this is dx dt squared plus dy dt squared, and this is how we find the arc of length. So this is the total distance traveled by the drone using the arc length, but we can't use the arc length, the formula, as in menu calculus. We need to use a different formula for the arc length with parametric equations. Another thing we can do, we can sketch the velocity graph, since I already have those defined. So that's the velocity graph, and we can do the same thing here, graph trace, and that's quite a nice feature here. I go 0, so this is my speed at 0. I mean, these are the components, and if I find speed square root 4, which is 2, and then if I go pi, and pi enter divided by 2, I get 1 and 3, so at this point the speed is square root 10, and if I enter pi, at this point the speed is square root 16, which is 4, which is actually the maximum speed for this particular drone. We could do the same with acceleration by differentiation x2 and t, and again we can see how the acceleration changes, and you can draw both on the same set of axes. So that's quite a few interesting things which can be done. And also, because this is our acceleration, you could use the calculator screen, and we know that for the speed we had x2, so we need to go, if I want to find the formula for the speed, x2 in t, and I take that squared plus bracket y2 in t, and I have that squared, so that gives me the expression for the speed at any time, which is 10 minus 6 cos t, and that's why we have the maximum speed as square root 16.4 and the minimum square root 4.2. And interestingly, if I do the same thing, but I change that to x3, so that will give me the magnitude of acceleration, which is 3, which shows that we have a constant acceleration here. So just a few nice features, how the parametric equations can be used and how can use different features there. So that is about drone flight. And next thing I would like to show is looking at Euler's method. So I have a PowerPoint here, and let's say we'll try to use Euler's method of numerical integration with a step size 0.1 to find y in 1 when y dashed equals y minus x and y in 0 equals 2. So Euler's method can be done in 3 different ways. We can do it graphically by sketching a differential equation field. We can use a spreadsheet. It's probably not that recommended for an exam unless they have something prepared, or we can use the calculator screen. So if I will go back and I will graph, and I want to use differential equation entry. So I have differential equation, and my equation is, I need to use y1 because that's what it's, y1 dashed minus x, and that sketches the field. If I open that again and enter 0 and 2 as initial parameter, then I can see the solution curve. Now, if I now go to trace again and graph trace, and I start at 0, and then using the right arrow, I can go to the required point, which is the point 1. This accuracy again might not be enough, so this is the value of y at 1 using Euler's method. So if I want the higher accuracy, again we can play with the same thing. So this gives me the value of y at this point. Important thing to actually point to the students are the settings. So solution method has to be Euler, and if we scroll down, by default the plot step is 0.1, which we had in this question, so it worked okay. But if the plot step is a different thing, of course they need to change it, and then it will skip whatever the step was. So that is using it in the graph screen. If we want to use Euler method in the calculator screen, again, if we start with U and go down, we can see that there is Euler very while here. And so it's quite complicated, the syntax, but that question will be on exam 2 and they can have notes, so we don't need to worry that much how to enter. But I have that pre-written in the PowerPoint. So we put the right-hand side of a differential equation, then we put independent, dependent variable. Then we use the curly brackets to put initial x value and final x value, then y value from initial condition, and then we put steps. So it does look complicated compared to actually the graphical method, but if we have the step 0.001 graphical method, probably wouldn't be that effective. So if I go there again and select Euler, and enter y minus x, x, comma, y, comma, and now I need to get the curly brackets, which are 0, 1, you step to get out of there, another comma, 2, and finally we put the step. That gives us the value. So using the right arrow here, we can actually do it because there isn't that far to get to the very last thing, which we get 4.5937. We can easily change the step once we have the entry there, and I change the step to here. And now if I press Control menu, it gets us to the very final bit, because going with the arrows to the right thing takes a while, so it's Control menu. And it's particularly useful if I have step point 1. So I need to get up there where the arrow is, and then use Control menu, and again I get this point with the step. So as we can see, the accuracy changes. So let's see what is the actual value. So to do that, we would need to use the solve. So we go calculus, differential equation solver, and we need to enter our equation y dashed equals y minus x, and then we enter our initial condition, y in 0 equals 2, and comma x, comma y. Well, I probably rather have Control enter, and something didn't work, as it usually happens, which might be some of the settings. I just did it before and it worked beautifully. And I don't, the y dashed and y0 equals 2, comma x, comma y. Anyway, the actual solution, I won't be going into, but it should work, is actually e to the power x. The calculator should return that, plus x plus 1. And if I want this value at x equal to 1, this is the value. So if we scroll and look, so of course this is the closest to the actual value which we would have there. The other method is using the spreadsheet, which is probably a good method to use when you teach how to do it, because if I go up here, so I have my x values here and then the y values there, and that step multiply times the y values, and you just enter different functions there and multiply by step, and then you copy everything down. So if we scroll to this point, that's the value we can get in the screen. So very quickly, last question, because we're running a bit out of time, is implicit differentiation, and Ray touched on that with a nice example. Now I have another curve which actually is x cubed plus y cubed is 3xyx greater than 0, and we want to find the equation of the tangent at the particular point. So again, I do the implicit differentiation, and I can find this value when I have the x and y value. So that's my equation of the tangent, and at what point the tangent is horizontal. So I can solve that, and I reject the first bit as it's both horizontal and vertical. And now I managed to draw it. You can't draw this function x cubed y cubed during the relation, but you could solve and redraw it, and then you can sketch actually using relation even unsimplified tangent. So it does show it's a tangent, and then if we look at those values, you can see that's vertical and horizontal. So that's all I had prepared. Thank you very much, and back to Rodney.
Thank you, Virginia. I was monitoring all the chats and questions tonight, and there wasn't any questions tonight, but that's like it's just such a wonderful job, you and Raymond. So we'll actually sum up of the night's proceedings and look at the Texas Instruments Australia website. So if you visit the Texas Instruments Australia website, obviously in the middle of the screen that jumps out at you is the future webinars. So if you click onto that there, and you will notice that tonight's webinar, here we are here, Virginia and Raymond, Exam Readiness for Specialist Mathematics, and then tomorrow night, the math methods, and the night after is the further, and you'll see the future webinars later in the year. So if people have missed the webinar or would like to see the recorded webinars, you'll click on the On the Demand tab. And for example, last week's webinar was John and Brian with coding the TI-Nspire, and you'll see the webinar. You can watch it online or can download it, save to an external hard drive. You can download all the TNS files and PDF documents, etc. that the presenters use. So as you see on the right-hand side, you'll see the list is quite exhaustive. It just goes on and on. So it's fantastic that Texas Instruments Australia keeps those resources there. Now, one thing that teachers need to look at, etc., you'll see if you click on the Teacher tab, at the top you'll see the Australian Curriculum Inspired, Senior Curriculum Inspired, TI codes, there's a lot there. So let's click on the Senior Curriculum Inspired. And as a lot of attendees tonight are Victorians, and we're talking about specialists, and you'll see some pre-prepared activities, TNS files, documents, etc. So if I click on Calculus, for example, just picking one out, and you'll see 3 examples there. So some has just been added over the last few months. So if I click on Solid Revolution, you'll see that what's in the actual document, and you'll see on the right-hand side, you'll see the PDF, you'll see the answers. That's a lot of teachers love seeing that. And you'll see the TNS file, or you can download them all in one hit by downloading the zip file. So it's fantastic resources from Texas Instruments Australia. Also, you might remind yourself of the YouTube channel. You'll see that in the the PowerPoint before the webinar started tonight. So if you see the youtube.com/user TI Australia, you can actually visit the YouTube channel, and you may click on the videos, and you'll see also the recorded webinars. So the option is obviously visiting the YouTube channel or the Australian website. Now, also, just as a reminder for wrapping up tonight, that everybody, if you get a chance to fill in the survey at the end of this webinar, and also look in your email inbox over the next few days, look for your email for the certificates so you can print off your professional records. So, thank you, Brajena.
Thank you.
Thank you, Raymond. Are you still there, Raymond?
Yes, thank you. I thought it was very good tonight. Thank you.
Lots was covered, I think, in the practice session that Raymond and Brajena had so much to share that we had limited time for 1 hour. So thank you for viewing, and we look forward to participation in future webinars. Bye for now.
Bye-bye.
Good night.